Okay. Oh, and we're missing Jesse O as well. So there's that. And yeah, so clearly we need to record this. There it is. Hi, guys. So we're looking at number 22 on page, what is that?
270.
270. And on page 270, we're told that we have a reservoir of water that is shaped like a hemisphere. Sometimes you get these crazy things in people's yards, you know? Just imagine this as a certain, a spherical bowl kind of sunk in the ground, and then they'll put like goldfish in it or something. And we create flesh. And what information are we told about this hemisphere? And it's filled with water to a depth of 4 meters. So that this is 4 meters right here. And if it had only been all the way full, then we could have taken the formula for the volume of a sphere and cut it in two, and we'd be done. But they didn't. So we're going to have to estimate. And so you began with a volume formula, and what is your volume formula? Times height. And this is the volume for a cylinder. So you are clearly thinking about taking your volume of water here and estimating it with a bunch of cylinders. In part A, that's exactly so. And then you took your volume formula, this is for a constant height, and you turned it into a Riemann sum formula by saying volume is equal to the sum from I equals 1 to n of pi times the Ri squared times the delta Hi, like so. All right? And so that's great. But now we have the important question, what are we going to use for the delta Hi and for the Ri? So, we probably want to start with a partition. We're going to use 8 of them, right? And so that means that we can immediately write that the delta H are all going to be exactly 1/2.
Okay, so that's delta H.
Yes, exactly
Okay.
so.
Okay.
Because what we're doing is we're taking our 4 meters and we're dividing it up into 8 equally spaced pieces. 1, 2, 3, 4, 5, 6, 7, 8. Kind of badly drawn, but there it is. 8 equally spaced pieces. And each one of these is now going to be the height of a pretty thin cylinder, like so. Okay? Now, the next question is, do I want to use a left sum or a right sum, or a midpoint sum, or a what, in order to find the radius? Whatever you want. And it makes sense to me that I might want to use as the radius the one at the radius of the top right here. And if I do that, then my cylinder is going to be one whose radius is defined by the top point. It's going to stick out a little bit beyond the sphere. That if I do this, then my answer is going to be larger than, guaranteed to be larger than the true value by a little bit. Does that make sense? Okay. And so if I do the radius at the top, well, the first radius is obviously, well, it's not obvious what it is actually. I have a bunch of heights, but I need a way to get from the height to the radius. That's the interesting math problem here. I can see that my various heights are going to be 4 and 3.5 and 3, and all the way down to my last height is going to be 0.5. But how do I get from height to radius? And so I think about this for a minute. And the mathematician thinks it's all constrained by the fact that it has to fit within the sphere. And if I look at a sphere in 2 dimensions, what shape do I see? A circle. Aha. And what is the equation for a circle? For a circle. No. Like the mathematical equation that describes the x's and y's in a circle. Yeah, that's right. X squared plus y squared is equal to r squared. And the x here is the radius of my cylinder. You see that? In other words, if I put axes on this guy, like this, and I go to some point on the circle, then the x value is that radius. And what about the y value? Well, the y value is this distance right here, which is clearly 8 minus the height. So that the y value is 8 minus the height. This is the key mathematical insight that needed to happen in order for us to cleanly solve this problem. So I want everybody to take a minute and think about it for just a second. We're taking our sphere, representing it in 2 dimensions as a circle. And we're seeing that these 2 things are true. Let's get to this relationship a different way using geometry. All right? If I have a height like so, and I have a radius like so, then it's pretty clear that this distance right here is 8 minus the height. And now 8 minus the height and the radius form a right triangle together with the radius of the sphere, which is 8. So that I can say that r squared plus 8 minus h squared is equal to 8 squared. So the key insight here is that in a sphere, everywhere you go on the sphere, there's a radius. And the radius of that sphere is 8. What this allows me to do now is to say that each Ri is going to be, and actually what I really need is Ri squared, right? So each R squared is going to be equal to 64 minus 8 minus h squared. So we can actually simplify this a little bit because this is 64 minus 16h plus h squared, so that when the dust settles, I get a somewhat convenient expression of 16h minus h squared as the radius squared. This is our first example of what's going to happen a whole lot with these areas, and that is that I'm representing one variable in terms of another so that I can substitute it. And in particular, because my height, my deltas were delta h's, it makes sense to represent everything in terms of h, because I actually know the h values, whereas I do not know the radius values directly. So I can now write that the volume is equal to, as you had, the sum from I equals 1 to 8 of, let me pull the constant pi to the outside, if that's okay with you. And now, I'm just going to walk through, and the Ri squared is actually 16h minus h squared. And my first height is 4. My second height is 3.5. My next height is 3. and so on, all the way down to my last height, which is 0.5. And all of this is times the delta H, which I computed before, which is 0.5. This is a pain in the neck to compute. Yes?
Why is M equal to infinity?
Oh, because I've been, thank you, because I have been doing infinite series with my Calc 2 students, and I was on autopilot.
You said 8 and I said
I said 8 and I wrote sideways 8. Sorry about that. Slight moment of panic. This was a sophisticated problem, and the sophistication about it was figuring out how to relate the R and the H. And the key to that was Pythagorean theorem. Does that make sense? Any other questions about this one? I have a question. I don't feel like I want to do all these computations by hand. Does anybody have an idea as to how I might make it a little bit easier for myself?
Integration.
What's that?
Integration.
Yes, but I don't know how to do that yet. How would I go about using a calculator in order to simplify my life a little bit? Awesome. Say that again much louder, and then we're all going to do that. So get your calculators ready, because here we go. I can do what?
Plug in the equation and go to tables and find what values there's square.
Ah, I agree. Walk me through that process. How is that all going to work out? Where do I begin in using the calculator to simplify the calculations here? Somebody help me. Because if we're taking this long to stall out, the calculator is not actually a useful tool, right? We need to be resourceful and savvy, not helpless and sleepy.
Table set and select what
Okay, so we're going to go to table set. Where do I find table set? So we have second table set. And what do I set on my table set? For what?
Where it says table start.
Okay. Equals 0.5. And this corresponds to my very first height. Good. Now what else? No, we need some more stuff besides just table start equals 0.5. What else do we need? We need the delta table, right? What does that delta table need to be? Also 0.5. The delta table is going to be my delta H, right? Good. So I've got that. Now, you said something about a function, so how do I enter the function? Y equals, that's right. And what am I going to make my function? Minus x squared. Why don't we just package our delta H of 0.5 into that, because we know that we're going to end up multiplying by 0.5 anyway. And so if I do that, now I have the whole kit and caboodle right there. And if I now look at second table, then I get a delightful thing. What do I get for my first y1 here? It's gotta be nice and loud.
12.174.
Does it give you 4 places?
12.174.
It just gives you,
Yeah.
it only gives you 3 places?
Yeah.
That's unfortunate. If you put your cursor on it, it will give you a couple more places there. And then you can kind of walk down through. 737. Okay. And then the next one is 41. 19. And then it goes all the way down until I hit the last one, which is at 4.0. Now, so here's what my computation would look like. I write the form here, and now I can directly write these numbers. Yes?
Is it, you put us out like everything.
Golly. And I can write out all 8 values right there. Kind of a pain. I would probably just leave it at that point. If I really want to add them all together to get a full value, I can do that. But it saves us a whole lot of the grunge calculations. Does everybody see how we use table and table set to simplify our lives a little bit? It's going to get better, even, when we actually do, as Matt suggested, do some integration. And that's today's topic. Does that help? Okay, and I think that gives you enough to do 24 as well. It's a matter of finding the delta H and then finding the radius. And you should be good. The radius is the distance from the curve down to the axis of rotation. That's okay. The key insight is to figure out what the radius is, and I'll let you chew on that for a little bit. The radius is constrained by the curve. Okay. Okay. So our story so far is that we had regions. And the region had bounding curves. Y equals f of x equals a, x equals b, and the x-axis, which is spelled y equals 0. And that region is this region right here in green. And our method for estimating the area of the region was to partition A to B into a bunch of delta x's, and then to choose a height from each subinterval, and to construct area is approximately equal to height times width, and add them all up. So that we ended up with a Riemann sum, which was the sum from I equals 1 to n of f of ci delta xi. What we liked a lot about this method is that it is very general. If you give me any region whatsoever, I can estimate its area. That's powerful. That's amazingly powerful. It doesn't rely on remembering specific formulas for specific shapes anymore. I can do it all. What I did not like about it was the fact that it was an estimate. I did not like the fact that I ended up with some error And you can see that error visually in some of the rectangles that we have here, especially when the curve increases sharply. You can see that just this little bit right here is an error in the approximation. And because that little green area is actually covered by the region but not covered by the rectangle, that error represents an underestimate of my area. Whereas over here, I have just a little bit of area right there that is covered by the rectangle but is not covered by the region. This error is an overestimate. All right, so the question is, what could I do about that? Well, in order to make that error as small as possible, I want to use as many rectangles as is feasible in order to shrink that error down to a very, very small number. Does that make sense to everybody? In other words, the more rectangles I use, the better the approximation. We in the digital age have a very good sense of that. This is precisely what it means to increase your pixel densities. How many of you have ever seen old school monitors that have like a 320 by 180 resolution or something like that? Have you seen those? The big blocky pixels, right? Some of us grew up on that. And so we were amazed when screens came out that were 1024 by 768. Because the pixels are smaller, because I have more pixels on those large resolution monitors, you can draw a line or a curve that really looks like a curve. Is it actually a curve? No, it's actually, if you magnify it, it's actually little tiny pixels that are block shapes. But if you get enough pixels, the eye really can't tell the difference, or at least it has a hard time telling the difference between the two. Does that make sense, everybody? So what we're going to do is to essentially try to use very, very large numbers of rectangles to make this happen. And so the cure for error is to let n go to infinity. We're simply going to say, let's take an infinite number of rectangles. Now, if we do an infinite number of rectangles, we would have to do an infinite number of calculations, unless we find some spiffy way around it. So our conceptual goal here is going to be to let n go to infinity. Then, having done so, the next question is, how in the world are we going to compute that? That's going to lead us to what is called the fundamental theorem of calculus. So our big picture goal over the next week and a half is going to be, we're going to figure out how to let n go to infinity so that we get exact values for the areas instead of merely estimates. So conceptually then, I can say that the area is exactly equal to this guy right here. The limit as n goes to infinity of the Riemann sum. And if you want to shorthand the notation here, you really can write this as the sum from I equals 1 to infinity, like that. See, I was just getting ahead of myself in the lesson. Now, way back when we did limits, to find slopes, to find instantaneous rates of change, we took a slope of a secant line and we let delta x go to 0. And when we did, we changed out our notation. In the Leibniz form, we took our capital Greek delta d here and we replaced it with lowercase English d's, just like this. And we called this dy over dx. Not that it's the quotient of two quantities that are 0, because you can't divide by 0, but it is the limiting case of the quotient as the denominator shrinks to 0. We're going to do a similar notational kind of thing for our sum right here. As we let n go to infinity, our delta x is going to shrink down to 0, because the delta x is b minus a over n for equally spaced deltas. And the result is that as n goes to infinity, delta x shrinks down to 0. And so notationally, we're going to replace the capital Greek S, sigma, for sum, with a stylized English S, like this, for sum. And we're going to replace our capital Greek delta with the lowercase English delta, like this, below. And now, let's have a clear picture of what's happening here. As delta x goes to 0, the width of my rectangle is now shrinking, 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 like this. And there is only one choice of x value in a rectangle of width 0. I have to choose the x value that I'm at. My subinterval shrinks down to 0, and that locates one specific point. Therefore, we're simply going to say that the x value of our choice is simply x, just like this. This is going to be our Riemann sum. And we call this a definite integral. Now, to make it definite, we need to specify what the total interval is, and we're going to do it like this. We're going to say that we're integrating from a to b. We are adding up height times width all the way from the first x, which is a, all the way out to the last x, which is b. And this is the notation that we're using, and it simply means exactly the same as this guy right here. And what it computes for us is the area under the curve, and as you saw from the video, we call that the net signed area, because any f of x's that are below the axis will count as negative values. So this is a very conceptual thing. We don't know yet how to compute the integrals, except that we can estimate their values with rectangles, right? That's the only thing we can do so far. We'll be able to do a lot more later on. Right now, all we're doing is writing the area as this definite integral. So our goals for today are twofold. First of all, we want to be able to take areas and represent them as definite integrals. And then the second thing that we want to do is to unify the concept by taking definite integrals, and if they happen to correspond to areas that we already know, to evaluate them using area formulas that we already know. So this is our first kind of a baby step into the definite integrals. All right, so let's do that. Let's see what this looks like. Let's say that I have a region that is formed by y equals x plus 1 and x equals 2 and x equals 4 and y equals 0. And so what I wish to do now is to find the area of this region, or to express the area of this region. So I begin with a sketch. I sketch y equals x plus 1, and the vertical lines x equals 2 and x equals 4, and the line y equals 0. And then I highlight it, just like that. There is my region. Ta-da! And now I'm going to express the area of that region as the sum, starting at x equals 2 and going all the way out to x equals 4, of height times width, which is the integral from 2 to 4 of x plus 1 dx. The height is x plus 1 because the height of my rectangle is from the curve down to the bottom, just like that. And the distance there is x plus 1, whatever x may be, minus 0. Does everybody see how I'm constructing that as an expression? You may be thinking to yourself, don't we have to put parentheses around this? And technically, yes, we do, because the width is multiplied by the entire height. However, the parentheses are usually implied or understood as being part of the outline. So you'll see it usually represented without the parentheses. Does this make sense to everybody? Okay. Let's do a second one. Let's say we have y equals x squared. We have a region which is defined by y equals x squared and x equals 3 and the y-axis. And what we wish to do now is to write an integral, write a definite integral that represents the area. So we begin by sketching the region. The sketch is crucial because the sketch is going to give us insight as to how to construct our integral. So we have a sketch of y equals x squared, the vertical line x equals 3, and y equals 0. And now I begin to understand why I didn't have a second vertical line there. It's because the region is cut off right at that corner, right at the origin. So, just to get a clear sense of it, I'm going to draw myself a small representative rectangle, which represents all of the rectangles that I'm covering my region with. And I'm going to write the width of that rectangle as dx, and the height of that rectangle is y equals x squared, like so. So that the height of the rectangle, so the area is going to be the integral then from the first to the last. What are my first and last? 0 to 3, that's right. And please notice it's pronounced 0 to 3 and not the other way around. And the height of that rectangle is going to be x squared minus the bottom, which is 0. And the width of my rectangle is dx. So I should be able to look at the integral and see the region sitting right there staring me in the face. I've got x squared as its height, I've got dx as its width, and I'm going from 0 to 3. Does this make sense to everybody, just in terms of setting it up? We're not worried about computing it yet. Okay. All right. Now what I'd like to do is I'd like to consider how we might go about computing some of these definite integrals if they happen to correspond to area formulas that we already know. I want to consider, for example, the integral from 0 to 5 of 6 dx. Could I actually evaluate this guy? Well, let me take the integral and create a region that corresponds to it. And I'm going to do it by the reverse process. I'm going to start by taking this as my height. And because that is my height, what I'm talking about is a constant height of 6 all the way across. And I'm going to take my limits of integration, 0 to 5, as vertical boundaries. And I'm going to take the y-axis as my bottom boundary. Sorry, the x-axis is my bottom boundary right there. And when I look at this region, I now say, hey, wait a second. This is a familiar shape to me. It is a rectangle. And the area of the rectangle is width times height, right? And so I get 6 times 5, which is going to be 30. When I'm doing this, by the way, I tend to write areas in the regions themselves, because if I have a complicated region, I might be able to split it up into smaller pieces, and then I would write the smaller pieces, the areas of the smaller pieces, and then just add them up. So that I can immediately compute this as 6 times 5, which is 3, just like that. Let's actually generalize this, and we'll get a kind of formula for these integrals. If I wanted to integrate from a to b, some constant k dx, then I would represent this as a constant k. Here's my height. And my bounding curves are x equals a and x equals b, like so. And my bottom boundary is the x-axis. And so now I recognize that I have a region that is a rectangle, and the area of that rectangle is height times width. What is the height of my rectangle? K. What is the width of my rectangle?
B minus A.
Good, that's right. It's b minus a. So that the area here is k times b minus a. And look at that. We have a formula. Our very first integration formula. We can integrate a constant as the constant times the width of the interval, b minus a. Does this make sense to everybody? Yes, sir.
Did you say dx is the width, right? Or represents the width?
Dx represents the width of each rectangle. So here, the dx represents the width of each rectangle that's covering the whole region. So I'm imagining starting at A and going to B in increments of dx. Just like that. Whereas the b minus a is the width of the whole thing added together. So you can think of the b minus a as all the dx's added together. Okay? So this was successful. Let's try branching out into maybe some other linear functions. What if I have the integral from, let's do this on a new page. What if I have the integral from 0 to 3 of x dx? Okay. So again, I'm going to sketch the region that this corresponds to. Everybody do that and see if you can come up with a number for this integral. Sketch the region, and then if you happen to identify a familiar shape, you're good to go. Okay. And what does your region look like? It's a triangle, absolutely, that's right. Y equals x is here. We go up to the vertical line, x equals 3. And now we have a triangle. And so we would, we can appeal to the area formula for a triangle, which is 1/2 base times height. What kind of height am I talking about for my triangle? Yep, the BF of 3, very good, which is 3. Yeah, that's right. And this guy right here has a width of 3, so what's the area of the whole thing? which is 9/2, right? Ta-da! Another integration. That's it. Sometimes the regions are surprising. So if I look at something like this, my first thought is, I have no idea. Right? But then I say to myself, let me sketch the region. Yeah,
This has an asymptote.
this doesn't have any asymptote.
No, but it's the same as that.
If there's a vertical asymptote, then you have what's called an improper interval, and you are going to learn how to deal with that until next year. What does the graph of y equals root 4 minus x squared look like? Hint, do a little bit of algebraic rearrangement. Square both sides. What do you get? Add x squared to both sides. What do you get?
A circle?
Yeah, that's right. This is the same as this guy right here, but it's only the positive half, the top half. And so my region looks like this. It is the top half of the circle, x squared plus y squared equals 4. And I'm pretty sure I know the area of a circle. What is it? Pi r squared. So what is the area of a semicircle? Half of that. That's exactly right. So that I can immediately write that as 1/2 of pi r squared. Now, algebraically, it is not obvious to us yet why this interval should have that value. It seems like dark magic. But, in fact, it's a simple consequence of the fact that the integrals represent areas. One more shape, and then we'll call it a day. So far, we've had rectangles, we've had triangles, we've had semicircles. I want to consider one final shape, and that's trapezoids. Like so. If we sketch this region, then the region that we end up with is the shape of a trapezoid. And the bases of the trapezoid are the two parallel sides, which in this case are the vertical lines x equals 1 and x equals 4. And the height of the trapezoid is the distance between those two parallel sides, which in this case is the distance along the x-axis, right? And we can think of the trapezoid as being a rectangle that has undergone some surgery. Because if I take my trapezoid and I go right to the middle here, which is the average of these two right there, so that'd be 2.5. And I cut my trapezoid at its average height, then I can see that this little triangle here and this little triangle here have exactly the same area. So that the area of a trapezoid is equal to the average of its two bases times the height. By averaging those two bases, I undo the surgery. I cut off the little extra triangle and put it into its missing spot. And I now create a rectangle whose height is the average, or whose distance this way is the average, and whose width is just like so. So that we can identify that we have a base here whose height is 2 times 1 plus 3 is 5. And we have a base over here whose height is 2 times 4 plus 3, which is 11. And the area is therefore equal to the average of 5 plus 11, or 5 and 11, times the width there, which is 3. Which comes out to 24.
What
Yes.
does dx stand
What does what?
A.
Oh, a trap. Yeah, sorry. My handwriting is sometimes bad. Good. Well, I'll see you guys tomorrow, and we'll do some more of this.